Hi friends, in this lecture what I'll try to do basically is try to take the concept of shear force and bending moment forward. Now essentially in the previous two lectures we have looked at the sign convention, right, and we derived a relation between the shear force, the bending moment and the intensity of load. We'll punch all those concepts up and try to move forward with those concepts. Now in this lecture what I'll try to do essentially is subject the beam to some sort of a transverse concentrated loading system and try to define a general shape of the shear force diagram and the bending moment diagram. I'll not try to look at specific examples, but I'll try to look at the philosophy and what is the basic principle that goes in behind drawing the shear force diagram and bending moment diagram for a case of transverse concentrated loads. For example, then suppose I have this is my beam and this is subjected to P1, P2, P3 forces. My reactions are R1 suppose and R2 suppose. Now to draw the shear force diagram or bending moment diagram, the first thing that one has to consider is that he has to define certain regions wherein the shear force diagram and bending moment diagram will be defined by only one equation, right? And here we will see that is there any change of some kind, that is this point doesn't have any transverse concentrated load, this region also doesn't have any transverse concentrated load. So between A and B there are no transverse concentrated loads acting as such. As such, I can take any section between A and B, right? And I can mark the internal forces to be Vx and Mx essentially, right? So what is Vx? Vx is the value of the shear force, right? And this Vx minus R1 will be equal to 0, or this Vx will be equal to R1. Therefore, at A, the shear force will be positive and will be equal to R1. Between A and B, there won't be any transverse concentrated loads as such. So therefore, we know that dV by dx, as this is equal to minus W, and W is equal to 0 between A and B. So essentially, this V will be of a constant nature. Right, so between A and B, the shear force will be constant. At B what happens? At B there is a transverse concentrated load in the form of P that will act. And essentially, therefore at this section, in the region defined by BC, I will have Vx minus R1 plus P1 to be equal to 0. Now Vx is equal to R1 minus P1. Right. So in this section between B and C, in this region between B and C, the value of the shear force will be again constant because there is no transverse concentrated load between B and C, but definitely at point B there will be a change in value of the shear force, and from R1 it now is equal to R1 minus P1. At point C there is a transverse concentrated load in the form of P2 acting. Now if I assume that P2 is greater in magnitude than R1 minus P1, then essentially this will decrease and this will come on the downward side of the axis. Then the positive shear force is represented in the upward side of the axis, the negative shear force is represented in the downward side of the axis. So at this point, that is just to the left of point C, we will have the shear force to be equal to R1 minus P1. Now at point C, there is P2 acting, and as such the shear force will decrease in its magnitude from R1 minus P1 to P2. And essentially if P2 is greater than R1 minus P1, then it will be a negative shear force. So for example, P2 is greater than R1 minus P1, so essentially this value is equal to P2 minus R1 minus P1. And this value is what I get at point C. Now between point C and D, there won't be any change in the value of the shear force because W is equal to 0, load intensity is equal to 0, and therefore B is constant. So between C and D again, there will be the constant value of the shear force. At point D again, I will have P3 acting, which is essentially downward. So essentially, this will be P3, right? And from D to E, again I will not have any transverse concentrated loads, and at point E due to R2, it will retract to this original position. But this is equal to nothing but is equal to R2, right? So this is the shear force diagram, and from this shear force diagram we can make one or two observations. First observation we are going to make is that between in a region defined by 2 points, right, if there is no transverse concentrated loads acting, then essentially we have constant value of shear force, because then W, or the intensity of load as such, will be 0, and therefore V will be equal to constant. The second observation that one can make is that there will be a point, wherein there will be a change in the value of the shear force. That is, the shear force will have a change of sign, right? And this point is defined by C. And the implications that this point has on the shape of the bending moment will be studied once we draw the bending moment diagram just after this. So these are the two observations that I make from this shear force diagram. The next thing that I am going to do basically is draw the bending moment diagram from this shape only. This is my shear force diagram, and I have a relation that is essentially dV by dx, or I should say, dm by dx is equal to V. So essentially, by this relation I can plot a BMD, right? Now, this is my positive value of the shear force, this is the negative value of the shear force. Now at point A, there is no bending moment as such. Why there is no bending moment at point A? Because at point A there is no resultant moment. There is only a reactional force, but there is no resultant moment as such, and as such the bending moment essentially at point A is 0, right? Because a hinge connection, this is nothing but, suppose this is a hinge connection. A hinge connection gives constraints in two directions basically, and it doesn't give any restraining moment. If in a fixed connection essentially, if the beam was like this, then essentially it gives two constraints, and there is a restraining moment, that is the resultant of all these forces acting, the resultant of all these forces that creates a moment will be taken by a restraining moment, and this is Rm, suppose, right? And this